the last lecture, I have give you this assignment to solve this Thevenin equivalent network. So in this, we have to find the Thevenin equivalent network across this A and B ports. So we have an dependent voltage source. It's the voltage dependent current source, and so we have here the potential V naught across this 8 plus J4 ohm. So I hope you have tried this problem, and now we see the solution of this problem. So to find the Thevenin equivalent, we apply the nodal analysis. So in the nodal analysis, we have choose this node 1 and node 2. So this is node 1 and this is node 2, and this is our reference node 0. So we apply the nodal analysis over node 1, and we see that the current is V1 is at higher potential, and the current is in fact is moving in this direction, and so here the current direction is in fact is from this direction. So all the currents are leaving the node because node 1 is at higher potential. So when we apply, so we have moved here this current, which is this current. This current is 0 minus V1 divided by 4 minus J2, and is equal to 5 plus V1 minus V2 divided 8 plus J4. So these are the correspondingly this current and this current. So we simplify this equation in forms of V1 and V2. Now we apply the nodal analysis at node 2. So for nodal analysis as V2, so these two currents, so this current is entering the node, and this current is also entering the node. And what about this current? V2 is at higher potential, so this current is leaving the node. So we have moved this part V2 minus V1 here, which is V1 minus V2, 8 plus J4, and we have the two currents 5 plus 0.2 V out here. So the value of V out is V1 minus V2. So we substitute the value of V out in this equation and simplify it to find the value of V1. So we take the value of V1 in this equation to substitute here. So we will have this substitution here. So we substitute the value of V1 here. So so we have this new equation here. So here you can see that this is in fact is converted into new equation. So we substitute the value of this V1 here. So here is the part, new part. All right, simplifying this, we will get the value of V2 and V2 is equal to VThave, and we will find its value. Next step, we have to find the value of VThave across these 2 points A and B, and that value is calculated by open circuiting this current source. And because we have a voltage dependent current source, so we apply a voltage source across this terminal of 1 ampere at the angle of 0 degree. Now we will find the value of first we will find the value of IS, and for IS we apply the nodal analysis at this point at node A. So IS current is entering and point 2 V0 current is also entering, and this current is leaving. So as IS is unknown, so we take this is minus 0.2 V0. We shift it here. It is minus 0.2 V0, and this VS voltage, Vs voltage at this point divided by this entire impedance. So this is 8 plus J4 and 4 minus J2. So we will have the value of the current in the network, this current value. So that current is taken here. So after applying the KCL, we have the value of Vs is equal to 1. So Vs value is 1, and also we apply the voltage divider rule to find the value of this V out. To find the value of this V out. And for this, we are not considering this network. So we are only considering this network, because at this point, the potential is the same Vs, and we apply the voltage divider rule to find the value of V out. So with the voltage divider rule, we will find the value of this V out, and we will have this value of V out here. Now we substitute this value of V out in this equation. So to find the value of IS, so IS is given here. So this is the value of IS, and now we find the value of ZThave by dividing Vs by Is. Vs is equal to 1 and Is is reciprocal of this. So we will have this value of ZThave is equal to 4.473 at the angle of minus 7.64 degree. Now we have find the value of ZThave for this network, and we have also find the value of VThave for this network, which is V2. Now we will go to the some circuits of op-amp. So for op-amp AC circuits, we know some properties of ideal op-amp, that the resistance across the input terminal is infinite and the voltage across the input terminal is zero. So we have this source. So how to solve this network that we are able to find this value of Vout? So we have this node 1 and this node is in fact node 2, and we have the reference node at this point is 0. Right? So we proceed further. So we have 3 at the angle of 0 degree, and we have the current of this network, that this current is entering into the network and all other currents are leaving the network. So we have this current 3 minus V1 by 10 here, and we have this current is V1 minus J5, or we can say V1 minus 0 J5, and we have this potential is 0 volt. So we have V1 minus 0 by 10K, and we have this output potential at this point V out. So we take V1 minus V out by 20 here. So this is the nodal analysis at node 1. So simplifying this equation, so we have all these values in terms of V1 and V out. So we have the simplified form of this equation given here. Now all the current which is drawn at the output of the op-amp is going back or fed back, and that current is passed through this node. That current is passed through this node. So uh, we can take the current, uh, take the two currents here, that is V1 minus 0 by 10, V1 minus 0 by V10. So this current is in fact this current is in fact is this current, and this current is equal to this current. So that current is entering into the node. So we have this current is equal to this current. So we have the node 2, which is at 0 potential. That is node 2, which is at 0 potential. So we will write the equation at node 2. So that current 1 is equal to that current leaving. So the value of V1 is equal to minus JV naught. So if we express this V1 in the form of V naught here, so what will happen, that we can simplify it and find the value of V out. So from this, we have simplified the value of V out here, and that value is given here, and we can express it in the form of time representation. So for another network, uh, we have to find the value of I naught and V naught. So again, we take two nodes here. One is V1 and the other is V2. So we apply nodal analysis from at node first. We will take the value of the equation in terms of V1 minus V out, right? And at node 2, we have taken this value of at node 2. So we will have taken this value and simplifying these two equations, we will get the value of V out is equal to 2 by 3 at the angle of minus 90 degree. Or we can write it in the form of time domain. So again, we have the value of V out, and the value of current is, as we know, that is the current V1 minus V out by J20K. So it is in fact I naught is fed back here as we have seen in the previous case. So that is that I naught is equal to V out minus V1 minus J20K. So we will substitute the value of V1 from, we have derived in equation 1 in terms of V out, and we will substitute it here, and we will get this value equal to minus J2 V naught. And by substituting the value of V out is equal to minus 2 by 3J, we will get it minus 4 by 3. And substituting this value of V out by V1 in I naught here, so we will get its value of that much ampere, and we can write it in the form of time representation. So that is mentioned here. So this is all about AC op-amp circuits, and now we will start today's lecture. So we have the AC power analysis. For AC power analysis, we must familiar with the instantaneous power and the average power. So how to calculate the instantaneous and average power? So what is the electric power? Electric power is the rate of change of electric energy transfer in the electric circuit, and its units is watt or joule per second. So instantaneous power is the power at one instant of time, and we can have its representation in the time domain if the voltage and time are expressed in time. So power is also the function of time. So it defines the value of power at any instant of time. So if we say that V of t is the function of Vm cosine omega t theta v, and I of t in the same way is Im cosine of omega t theta I, both represented in cosine form, and we have the product of two A's, Vm Im, and the corresponding cosine terms. So we apply the trigonometric identity here because that term is equal to alpha and that term is equal to beta. So we have the trigonometric identity here that cosine alpha cosine beta is equal to 1 by 2 cosine alpha plus beta plus cosine alpha minus beta. So that will give you two forms, cosine theta minus theta I minus theta v, one term, and one term with 2 omega t theta v plus theta I. So we divide this in two parts. One is the time independent part and other is the time dependent part, because here the omega t is the time representation of the signal. So we split it. Here there is nothing about time, it's a constant term. So the time dependent part oscillates twice as much frequency as the voltage and the current waveform oscillates, because you see that this is in fact is a function of 2 omega t. So that too will twice the frequency of oscillation of the power. And how we can express this, if we see that the period or period of the instantaneous power is reduced from t to t by 2, and that u line shifts the power up to this constant term. So this is the time independent part which is given here. So that will shift this from 0 to that will shift this from 0 to up to this part, this blue line part. This function is shifts up to this part, and the amplitude and peak is given by this relationship, which is a function of time. So this is given by this relationship. So what is the concept of negative power? So in fact, power is absorbed by the circuit, but we have the power transfer to the network, and that power is mentioned by the negative sign. So if there is a source which is delivering power to the network, so it means the power is in negative. So it is transmitting negative power. So negative power means that it is power supplying to this network. And the power is consumed by this, by the resistive component of this circuit. So how it is possible that the power is transferred by the network? So power is transferred by the network because the capacitor and inductors store energy. So instantaneous power is changes with time. So we therefore calculate the average power, which is easier to measure. So we measure the average power in watts. So we take the average of the instantaneous power over one period. So if we take it for one period, so that is in fact is the average power. Now see that how can we take the average power for one period. So we have the two parts. So we take the average of the first part and the time dependent part. So it will convert it into the sine form after integration. And the sine of 2 omega t, or the sine of uh, uh, 2 omega t will be in fact 0, whatever how many multiples of 2t you are taking. So in fact all these multiples are 0. So this term reduces to 0. So we will take the average from this part only. So we will take the constant. So that term is constant and this t will cancel this t, and we have only the average power left is given by 1 by 2 Vm cos theta v minus theta I, right? So the average power is in fact is measured in this form in phasor representation. So minimum the phase difference, if say this phase difference is 0, then cosine of 0 is equal to 1. So we have the maximum power transfer to the network, and that power is equal to that component only. So we can find the instantaneous power only when the voltage and current in time domain. So instantaneous power is calculated in time domain. But the average power can be calculated in time domain and in frequency domain as well. So we can write the equations in phasor forms. So this is the phasor representation of voltage and current, and we have the VI product here, which is theta V minus theta V plus theta I, but we have to take the conjugate of this. So it is theta V minus theta I. So if we see that we have to take the VI conjugate, and we know that half of VI conjugate is equal to this relationship, and we have write this in exponential form, and the exponential form using Euler's formula we can write in sine and sine form. So we can therefore write the average power in 1 by 2 real VI conjugate is equal to the expression of average power transferred to the network. So here is the relationship with the average power transferred to the network. Now if the circuit is purely resistive, so we have theta V is equal to theta I. So what will happen that 1 by 2 Vm Im is equal to 1 by 2 Im square R, or that is equal to 1 by 2 I square R. But in case of resistive and capacitive component, theta V either leads current by 90 degree or lags current by 90 degree. So in case of inductive circuit and capacitive circuit, if we have purely inductive circuit and purely capacitive circuit, and in this case we have this equation, right? So any question up till now? So I hope you are clear about it. So you proceed further. So we want to say that resistive load absorbs power and reactive load does not absorb power. So that is the important property, and we will see it in an example. So first we are considering voltage and current values, a source supplying a current at this voltage to this network. So, and the values are given here. So how we calculate the instantaneous average power? So instantaneous power is calculated in time domain. So we have used this identity, we multiply it, and we use 1/2 cos alpha plus beta. It is the time domain part, and cos alpha minus beta, it is the time independent part. So the time dependent part is given by this. So we have this value is 385.7 watt. So what about the average power? Average power, we find it in the phasor form. So we have the current conjugate part. So the current conjugate part is here. So 15 minus 30 degree is converted to plus 30 degree. And we have half real of 1200 at the angle of 50 degree. So that value is 385.7 watt. So it means that the power supplied to the network is equal to 385.7 watt. So now we consider an impedance. So for example, we see that the impedance of the network is 20 at the angle of minus 22 degree, and the current supplied to the network is 10 at the angle of 30 degree. So first we calculate the voltage across this impedance. So the voltage across this impedance is IZ. So that is multiplied and we will get the value of 200 at the angle of 80 degree. Now we have this value of current and this much voltage. So we apply and simplify it to get the value of 927.2 watt. Now I left few examples for you to solve, and I will discuss these examples in the next lecture. So you have to study this and you try to solve these examples, and after this we will discuss it in the next lecture. Thank you very much.